We have need for a mathematical operation that computes the product of the perpendicular parts of two vectors. We're going to call this operation the cross product. And throughout this conversation, it would be a good idea to keep in mind the operation we have already learned, the dot product, which finds the product of the parallel parts of two vectors. The dot product is also known as a scalar product because it takes two vectors and produces a single number out of them, a scalar. Okay, so a cross product is in some ways the opposite of a dot product. Instead of finding the product of the parallel parts of two vectors, we now want to find the product of the perpendicular parts of two vectors. So here I've got an example vector A and B, and here the same A and B once again. And if I want to find the part of A that is perpendicular to B, I can draw it on this diagram by making A the hypotenuse of a right triangle. This leg would be what we'll call A perpendicular, the component of A at a right angle to B. And we see that the magnitude of A sine theta gives us the size of that component right there. We can also find the part of B that's perpendicular to A. So same two vectors, but here in this picture, I've made B the hypotenuse of a right triangle and drawn in those legs. And this leg here is the component of B that makes a right angle to the direction of A. So that's B perpendicular, which we see is given by the magnitude of B sine theta. So either way, if I want to take the perpendicular part of A and multiply it by the magnitude of B, or take the perpendicular part of B and multiply it by the magnitude of A, if I want the product of the perpendicular parts, we see that that is given by the product of their magnitudes and the sine of the angle between them. The angle that we get when we put the two vectors tail to tail, that's the angle between them, sine of that angle. So AB sine theta. We call this the magnitude of the cross product or the vector product of the two vectors. We call it the vector product because it takes the two vectors and makes a new vector out of them. Now, this is just the magnitude of that new vector. We'll have to discuss a little later the direction of the new vector that we get. For the moment, we'll just focus on the magnitude of the cross product, the magnitude of the new vector. In some branches of mathematics, this is also called the outer product of vectors A and B, as opposed to the dot product, which is known as the scalar product or the inner product for comparison. Notation-wise, the cross product is denoted by using this X or this cross, this multiplication symbol like you first learned multiplication in elementary school. This is A cross B, not A times B, but we say A cross B. So the dot in dot product, we say we're dotting A and B. Here with this cross, we say we're crossing A and B. But we have to be more careful with the language. We have to say A cross B, because as we'll discover, A cross B is not the same thing as B cross A. We'll get there in a bit. So anyway, A cross B is going to define some new vector. The magnitude of that new vector is given by this expression, AB sine theta. So we see the magnitude of A cross B would be the same as the magnitude of B cross A. Flip A and B here, and we get the same value in this case. So for example, let's consider two vectors R and F, the position vector and force vector with these magnitudes, 3 meters and 8 newtons. And suppose they have angle theta between them. Let's find the cross product, R cross F, for the following relative directions. Suppose first that they are parallel to one another. In that case, R cross F, the magnitude of the cross product is given by RF times the sine of the angle between them, that being 0 if they're parallel to each other. Sine of 0 is 0. What is the product of the perpendicular parts of vectors that are parallel to each other? 0. They have no perpendicular parts. Okay, so if, however, the angle between them is 30 degrees, some acute angle here, and that would be this angle right there, which we would get if we put R and F tail to tail, like extend R out this way. I ended up tail to tail with F, the angle between them being 30 degrees. In this case, the magnitude of R cross F is given by 3 meters times 8 newtons times sine of that 30 degrees, which is a half, so 12, and the unit would be meters times newtons, meter newtons, 12 meter newtons. There it is, 12 meter newtons. Next case, what if they are perpendicular to each other? Theta equals 90 degrees. If they make a right angle to each other, then their cross product has a magnitude given by 3 meters times 8 newtons times sine of 90, which is just 1. So 3 times 8, 24 meter newtons. The magnitude of the cross product here, note, is double the magnitude of the cross product here, because in this case, the vectors are more perpendicular to each other than they are in this case. And the more perpendicular they are, the greater the magnitude of their cross product. If we continue to increase that angle to 150 degrees, let's say, so that the vectors are opposing each other, we extend r out this way and find the angle between those two vectors as if they were tail to tail. That's that 150 degree angle. Then the cross product of this r and f has a magnitude given by 3 meters times 8 newtons times the sine of 150 degrees, which is 1/2 once again, positive 1/2, so this is positive 12 meter newtons. The same value as in the case when they were 30 degrees apart. So note that interesting property. These two vectors have a cross product of the same magnitude as these two vectors, both positive, both 12, and smaller than this case because now they are less perpendicular than they were when they were at a right angle to each other. If they are anti-parallel to one another, 180 degrees apart, so r points this way and f points exactly opposite it, then the magnitude of r cross f is r times f times sine of 180, which is 0. Anti-parallel vectors have no perpendicular parts. The cross product is 0. This raises a question: what happens if you try to cross a vector with itself? So using f from the above example, let's find f cross f. So f is parallel to itself, so f cross f would be the magnitude of f times the magnitude of f times the sine of the angle between it and itself, which is 0. Sine is 0. A vector is, of course, parallel to itself. It has no parts perpendicular to itself, so the cross product of a vector with itself is 0.